Over the past several segments, we've been spending quite a time talking about equilibrium and how it applies to weak acids and weak bases. But obviously, there are lots of kinds of chemical reactions that don't necessarily involve acids or bases. We're now going to talk a little bit about how equilibria apply to cases of solubility. Now, when we looked at delta G, we were able to think a little bit about when it would be favorable, based on entropy and enthalpy, for a compound to dissolve in solution. But the challenge we were always running into with delta G was that that was under standard conditions. And in particular, that meant 1 molar solutions. Quite apparently, there are lots of things that will not dissolve in solution up to a concentration of 1 molar. So the question becomes, how do we address or deal with those systems? With acids and bases, you likely noticed that we went from Chem 103, where we described them somewhat simply in terms of either being weak or strong, to understand why they were soluble, and ultimately use values like pKa to characterize their quantitative degree of acidity. In solubility, we're going to be doing something very similar. Lots of things that we would describe as not soluble are still perhaps just very, very slightly soluble. Back in Chem 103, we divided this between things that were either soluble or insoluble. But what we're going to see is that that's about as simplistic as describing acids as strong or weak. So, when you're thinking about some compound that's sitting in a solution, let's say water, perhaps some small amount of it dissolves. How do you determine what that amount is? That's ultimately the question we're trying to answer. As we're introducing this, I want to motivate it a little bit, because your first thought might be, well, what do I care about solubility? I want you to think back a couple years to the Flint water crisis. This was a case where the city of Flint changed its water supply, and in doing so, wound up giving a lot of people lead poisoning. What we're going to be seeing is the chemistry behind why that happened. In that particular case, the new water source had a higher concentration of chloride ions than the old water source. The result was that lead pipes in people's homes that had previously been quite insoluble were now just slightly more soluble. Now, back in our Chem 103 terms, we would still probably call that insoluble, right? That is, pipes weren't literally dissolving up inside people's houses and going away completely. But they were soluble enough that lead levels in the drinking water rose to the degree that there's a generation of children who now are going to have neurological issues because someone didn't pay attention to their solubility chemistry. So, with that rather dire introduction, let's look at an example reaction. In this case, we're going to look at another somewhat famous dangerous metal ion that can be in solution. That compound, or that ion, is chromium-6. Chromium plus 6 is a very powerfully oxidizing metal ion and was often used for that purpose. There's a town in California that was poisoned by chromium-6 that was leached into their groundwater by basically the local power company. So again, solubility is one of those concepts that winds up being very, very important, particularly if you want to avoid issues in the environment. So let's look at an example with that chromium-6. So this is chromate. Silver, you might recall, has a +1 charge. 2 of those must mean that this chromate has a 2- charge. If we look at formal oxidation states, each oxygen in that chromate structure should have a -2 charge, meaning this is chromium 6, the dangerous one. Now, if we were to put this into solution, we would expect to have this reaction occur. A quick note on how we write our chemical reactions for solubility problems. You might notice here that I wrote this in terms of something dissolving. That is by convention. We're doing this convention ultimately so that we can find equilibrium constants related to dissolving and use those from a table. This is very similar to the same reason that we always wrote our weak acid equilibria in terms of the weak acid dissociating. We're writing this in terms of dissolving for the same reason. So let's take a look at how we would write our equilibrium constant for this reaction. Now, equilibrium constants for dissolving processes get a special name as well, KSP. This is the equilibrium constant for dissolving. So, what needs to go into this equation? Well, we're going to have a couple of products here. Now is a place where those powers that we used previously come up. Does anything else need to be in this equilibrium expression? So this is the thing that's a little bit odd about solubility. This is a solid, and if you recall, solids don't appear in equilibrium constant expressions. That means that KSP depends only on the amount of products in solution. That means that there is a maximum amount that can be dissolved, but not a minimum. When we were looking at weak acids and weak bases, because the products and reactants were linked together through that equilibrium expression, you were required to have some amount of each. You couldn't separate them. In this case, however, because the reactants don't appear in the equilibrium constant expression, you can add as much solid as you want, but once the maximum amount has dissolved, that's all you're going to get. However, that also means that you can be below this limit. This equilibrium is only true when the solid is present or just barely present. That is, you can imagine sort of just the moment before solid would form. That's really weird to think about, right? The solid has to exist in order for this equilibrium to be true, but it doesn't appear in the equilibrium expression. That rather unintuitive aspect is one of the reasons that solubility problems can be a little bit tricky. But of course, you can dissolve less than this maximum. Remember, equilibrium won't always be true when you're dealing with solubility problems. So, another way to put that is that this only applies to saturated solutions. The last thing I want to mention during this introduction is that because each of these ions in this solubility equation could be provided with other counter ions, we could add in, for instance, some silver nitrate to add just silver, or some sodium chromate to add just chromate. Because we can add each of our ions separately, we can adjust the solubility of one ion by changing the concentration of the other one. We're going to be looking at that and more in our next segment.